So one thing I would like to mention, the topic I've changed the topic. So right now it's design of bridges and construction considerations. So it's more general in terms of bridges and what considerations we need to do during detailing and keeping construction in our mind and making sure that the design is constructible. So as Himi mentioned, I have 15 years experience. I currently working as a bridge section manager in HDR. HDR has more than 100 plus offices throughout US. We are global firm. I manage bridge group in the Tampa office. I have more than 14 bridge engineers from junior to senior engineers. I recently did MBA from University of Florida, but my roots are mainly structural engineer. I'm a structural engineer by heart. I have experience in concrete, prestressed beam bridges, steel plate girders, segmental bridges. Segmental bridges are my favorite bridges, post-tension structures. In fact, the first slide, if I go back, the structure on the right, that's a superstructure I designed connecting two islands in North Carolina in USA. Multi-column piers, hammerhead piers, post-tension straddle bend, those are all substructure elements supporting superstructure, whether superstructure is made of concrete or steel. 2-3 years ago, I did a seismic design with my team for a automated people mover project in California, in Los Angeles. That design was pretty neat in terms of the complexity, and that was the first time being in Florida. We don't design bridges for seismic. We design bridges for hurricane. I'm sure you must have heard recently about hurricane event in Florida, but that's what we design our bridges for. But California is a big seismic zone. So first, I would like to introduce you to some of the general projects you may be hearing these days. Like, so typically there are two type of projects. One is we work directly with our clients, and clients could be private clients and public clients, but typically we work with public clients. Which is mainly Department of Transportation, whether it's a Florida Department of Transportation or any other state Department of Transportation. Like I said, HDR has more than 100 plus offices throughout US. But we also work with local municipalities and local corporations. So we do design directly for them. Once the design is done, they let the project and the project contractor bid on the project. Those type of projects are called as design bid build projects. Then there is another type of project which are very common these days, are design build projects. So design build projects are basically design consultant teamed with contractor, and that's a joint venture, and then they go after the project. And Department of Transportation, our clients pick the team based on technical score and pricing. So they call it an adjusted score, which accounts for both technical score and bid price, and that's how they decide which firm and which team is going to get the project. So those are design build projects. Those projects are very common these days because it's fast-paced delivery, but it has more challenges to the design firm, and it brings tremendous amount of liability to the design firm. Contractor has a major skin in the game as well, because there is a delay penalty in terms of, if I put in dollars, it's like $100,000 a day, which is almost 70 lakhs, 80 lakhs Indian rupees a day. That's a penalty imposed on the contractor for a delay. If the delay is due to unforeseen conditions, obviously it doesn't account for it, but any other delays will incur tremendous amount of penalty. Then there is another type of projects like P3 project, which is part of the kind of like design builds, but those P3 projects are like clients are looking for financing as well, maintaining those assets as well for longer duration. So design build firm will come up with a, they will have a partner who's financing the project as well, and who's going to manage and operate the project for the Department of Transportation for longer duration. So that's those are basic the general projects we kind of chase in US, and I'm sure there is it's similar setup in India. I don't have any design and industry experience in India, but I'm hearing these days it's pretty much similar setup there as well. Then in the traditional procurement processes, what we typically do is we submit our letter of intent. We call it here LOI. So we submit our proposal, basic proposal, our qualification, why we are qualified for a particular project. Then the client, the Department of Transportation, they shortlist firms, whether they shortlist 3 firms, 4 firms, depending on the size of the project. Typically, at a minimum, they shortlist 3 firms. Then those shortlisted firms are invited for presentation, and then we do the final. We then based on the technical score, obviously they award the project. But the presentation, we it's a comprehensive presentation about how we see the project, what are the challenges we see in the project, how we going to overcome those challenges as well. So it's a comprehensive summary of the project we put together in roughly 50-60 slides. It's almost like an hour presentation to department. Then once the project is awarded, then the next step in the process is now you need to negotiate the overall fee for the design. So the way we do it is department uses their general engineering consultant. It's another firm who is part of, who has a contract with the department. HDR, my company, has a contract as well with our local clients. So we do the scoping for other projects as well. The projects obviously we are not chasing, but other company is going to prepare the staff hours and scope for the department, and then we as a design consultant we're going to prepare the staff hours as well. Those staff hours are man hours, what it's going to take to design superstructure of the bridge, substructure. We go detail by detail into like what it's going to take for pier analysis, abutment analysis, all those. We go into very deep into the detail of every single thing, and we specify why this pier design or so and so design going to take that much hours. So we explain everything, and then we come to the negotiations table, and then obviously we need to, as a design consultant, we need to justify why we need more hours to do the work. Once the overall staff hours are negotiated, then the next step in the process is we distribute those staff hours into different employee classifications. So DOT has a classification like principal bridge engineer, chief bridge engineer, senior bridge engineer, engineer, EIT, we call it, those engineers or undergrad degree holders or master's degree holder who doesn't have a professional engineer license. We call them as a bridge EIT, engineer in trainee, and then CAD technician. So then we distribute those total hours into different classification, and then DOT has rates assigned to those classification based on our multiplier, and the multiplier is different for each and every company depending on their overhead. So typically the multiplier is ranging from 3 to 2.9 to 3.2 something, and on an average it's like $60 an hour we get. We call it unloaded rate, and times 3 is like $180 an hour is roughly we get from the client. to do the work. Um, then obviously when we do the work, we follow codes which we need to follow. We cannot just simply design based on anything in our past experience and this and that. We need to follow the codes. The very first code for us on the left is ASHTO LRFD bridge design specifications. That's like a Bible for us. That's what we do. We follow chapter 3, 4, 5. Basically, chapter 3 is for loadings, 5 is for concrete, 6 is for steel design. So that's our Bible for bridge design, and that any bridge engineer throughout the US uses this code. Then every state in US has their own additional requirements, because obviously geography changes, and like California has a seismic design, Florida doesn't have a seismic design. So Florida Department of Transportation, FDOT, has put together their own criterias and guidelines which we need to follow on top of ASHTO. So the very first thing we need to do is to make sure those guidelines are met. And sometimes those FDOT guidelines overrule ASHTO guidelines as well. FDOT has construction specification as well, which kind of tells contractor how they need to deal with certain construction issues and what they need to do for certain construction, how things needs to be done and followed as well. So they have a comprehensive spec package which contractor has to abide by during construction. So let's talk about the type of bridges. I'm sure you have seen concrete bridges. Those who are in Delhi area, you have seen Delhi Metro is mainly running on segmental bridges as well. Those trapezoidal box bridges with post tension, those are precast segmental bridges. Uh, so typically the concrete bridges, we say pre-stressed beam bridges, those are pre-tensioned beams. Those beams could be box beams, I girders, U beams, but typically uh, we use our ASHTO beams. And then 10 years ago, Florida Department of Transportation came up with their own I girders, which is Florida I beams, which is a different shape than ASHTO beams. But those are typically pre-stressed beams are I girders. And then segmental bridges are mainly cast in place post tension structures, where the structure is constructed on false work and they post tension once the concrete hardens. And then, like I mentioned, Delhi Metro bridges, those are precast post tension structures, most of those bridges. And then extra dose bridge is a spatial type of bridge where most of the post tensioning is external as well. It's a hybrid form of cable stay and segmental bridges. Cable stay, the tower for the cable stay is pretty tall, uh, almost I would say 150 feet, so almost 50 meters roughly. And segmental bridges where all the post tensioning is internal. Extra dose is a combination of internal post tensioning and external stays as well. So the beauty about extra dose bridges is the tower height is less than what's required for truly cable stay bridges. The photo on the right is the structure HDR designed in Miami, Florida. It's under construction right now. It's a rendering of a bridge. Then steel bridges. There are steel plate girder bridges, which are very common throughout US. Steel box girders, steel truss bridges, and steel tied arch bridges are not very common, but mainly steel plate and steel box girders. And even in India, I've seen some of the bridges are steel plate girders as well. But mainly, I think it's concrete bridges, which are very common in India. These are this is from project I was involved with. All the slides I'm going to show you today is what I've worked on. So please feel free to ask me any questions. I'll be more than happy to answer. Hopefully, I can answer all those questions. But this is a multi-level flyover with steel box girders and steel plate girders, and that's kind of projects you deal with, because of now we are in a situation where our population is heading towards our main cities like Delhi, you see Chandigarh, you see now all those cities around. It's very packed now. So how you deal with the traffic congestion? So now instead of spreading the bridges around, you stack the bridges on top of one another. So you see second level, third level, and the fourth level structure over there. Those columns are roughly um, in meters is roughly around 25 meters tall. Those columns, roughly 80 feet tall columns for fourth level structure. And obviously the footing for those structures are pretty massive. It's and think about the construction and maintenance of traffic, MOT we call it. It's pretty critical, because that's one of the key for any project, is to maintain the traffic during construction, and on top of it maintain safe traffic. That's the key thing. So MOT for these type of projects is very critical and very complex, to make sure how the traffic gonna flow as things are getting constructed, and traffic gonna be moved on to the newly constructed structure. So it takes a lot of effort and a lot of involvement from great engineers to put their heads together and resolve those issues. And thinking ahead of those things during design. That would be my theme for this presentation, is we designer have we need to make sure we think smart, and we think comprehensively, and coordinate with other disciplines. So this work is not just structures or bridge work. It's a coordination with roadway, coordination with drainage. So that's how civil engineering is defined in US. Is we have different disciplines. Bridges, there is separate discipline. Then you have a separate discipline for roadway design, drainage design. Obviously they make sure the water gets conveyed from the bridges down to the ground and collected in the drainage pond. You can see right there is a drainage pond which was created to collect the water, obviously. And then traffic, they make sure the traffic signals and any signs they need to convey the traffic, and to make sure traffic flow is nicely maintained. And then environmental is another discipline, where obviously they make sure the construction and the life of the project doesn't affect the environment. So they acquire required permits. That's a comprehensive collaboration goes on every single project, and all those discipline I mentioned are always, most of the time they are always involved on any new project. The photo on the left is the project. Again, that segmental bridge connecting the two islands. It's almost 3,500 foot long structure, so almost 1,000 meters more long structure with 350-foot spans. So it's almost 100-meter spans, 110 meter span there, precast segmental construction. The two photos on the right, the one in the middle is a cast in place construction of the post tension structure. That's a structure which is in construction, almost done, for Los Angeles Airport, for Olympic Games in future. They Los Angeles Airport had a big expansion. The photo on the right is the rendering of the finished product, what it's gonna look like. So that kind of, obviously, that's a demand from the client, is we want to see how our structure gonna look like, how our final product gonna look like. And because they need to have a buy-in from the community as well, because eventually community is, we are using taxpayer dollars to fund the project. So obviously they need to have buy-in from the community as well, and from the client, that yes, this structure is pleasing to them. um, so that's a detailed submittal and information we provide to the clients, to make sure they are okay and satisfied with our final deliverables. So typical bridge design includes, so what are the basic steps in the bridge design? So first, geometry is everything. You need to make sure when structure elements are complex, because you are solving complex problems, which is the traffic congestion. Everywhere you go, whether you are in India or US major cities, you have traffic congestion, and traffic gets backed up for an hour or more. So we need to make sure we understand the landscape, and where the column, where our substructure gonna go, and how the superstructure gonna tie into the roadway. So the bridge geometry is the basic thing, but it's very important thing to make sure, because you design something, but the geometry, someone computed the geometry, and bridge is 1 meter higher than the roadway, then it doesn't make sense. So very first thing in the design process we do is, we set up our elevations, substructure elevations, and finish grade elevations. Then we use those elevations to come up with the column height, and all the good information we need to use for the design. So the next step is superstructure design. So superstructure design, there are key elements like deck, where we drive car and vehicle on. That's a deck. Then we have beam design. Like I said earlier, beam could be concrete or steel. Then we do the load rating of the beam to make sure that the beam is load rated for different type of vehicles. So for design, in US we have from ASHTO, it's a HL93. I'm sure there is a parallel vehicle notional load, we call it, in Indian code as well. Um, we design structure for notional load. Then we load rate the structure for additional permit vehicles, because every state has their own permit and legal loads, depending on the needs, what they have seen, long truck trailers, and so they have defined legal loads and permit vehicles. So we need to load rate those vehicles as well. And there is a different load factor. So load factor is basically when you compute the load, you apply factor on top of it, which is from the statistic analysis. They have figured out that there's a load factor we need to apply on dead load, we need to apply on live load, and all those factors are properly defined in codes. In ASHTO code, in here it is properly defined that for dead load you need to apply 1.25, for live load you need to apply 1.75, so and so on. And I'm sure you have seen same thing in over there as well. So we once we do the load rating, we want to make sure as a designer that the load rating is more than 1.1, 10% additional. And the reason we do it, because during construction things can change, contractor. So between the deck and the beam, there's a thickness of concrete which we call haunch buildup. Two different terms, but two terms for the same item. Some uses haunch, some says buildup. It's on top of the beam. So sometimes in the field, you may find out that the buildup is more than what you anticipated and what you computed based on the programs. Or due to some construction, not issues, but due to construction technique, let's say the buildup is more now. So if you don't have factor of safety in your design, that additional safety from your engineering experience, then if you're designing the beam for a rating of 1.0, if you need to assess the structure, the beams for additional loading in the field, it may fail. And obviously it's a costly, yes, it's on contractor, but it's a cost to the contractor. So typically we don't like to design to that refinement that rating is 1. So my experience has been always like to design it to at least 1.1 rating, 1.10. So at least you have roughly 10% additional safety for any field changes or anything happens in the field. Bearings are typically elastomeric pads, or sometimes those are big for segmental bridges. Those are big multi-rotational bearings, disc bearings. We use those are for heavy, big boys like segmental bridges and cable stay bridges. Substructure design. There is abutment design. So typically in US we put abutment on piles or not on spread footing, mainly in Florida because it's just a soft sand here. We don't get limestone pretty shallow, so it's mainly piles. Those piles can go up to 100 feet easily, so roughly 30-35 meters easily in the ground. And then we get the capacity on those piles due to skin friction. And so typically we put drill shafts, and obviously drill shaft sometimes is end bearings. So if we find the limestone layer 40-50 feet in the ground, so roughly 15 meters in the ground, then we use drill shaft. But drill shaft construction is expensive, so typically bridges utilizes piles. Then pier design, pier types. On the bottom of the screen, I'm showing straddle bend because it's straddling over the roadway underneath, and it's a complex pier. It's not a normal pier by any means. It's not regular day-to-day design. Those projects are rare in terms of once in 2 years. But lately, due to traffic congestion, where they need to put many roads here and there and many bridges, you see these type of piers are becoming very common. These piers are reinforced concrete pier caps, but this one on the screen and on the bottom, it's roughly 130 feet long. So again, we are talking about around 40 meters. Column to column is 100 feet, so roughly right there 30 meters. And it has post tensioning in it. The one on the top right is a C pier supporting integral steel plate girders, and it has a post tensioning in pier cap as well. The one on the left right there, this one has, these are hammerhead piers looking like a hammer. And then just further in, you see multi-columns there. So those are multi-column piers. So typically for substructure is hammerhead pier, multi-column pier, straddle bends, rare, and C piers are rare as well. And those are mainly when obviously the superstructure is over the roadway underneath. and you cannot obviously put the column on top of the roadway, and that's the reason C piers. But these C piers are very complex because you need to make sure the tension doesn't get developed on the back side of the column, and it it requires proper detailing and of the reinforcing to make sure the reinforcing is very close, the main reinforcement is very close to the tension face, which is the back face. In this view, this is the near face and this is the back face, so this face is where main reinforcement is, and I'll show you the reinforcement detailing for these piers and straddle bends. So typically, what we do is this is a typical section. This is what client says, like, okay, our current this is a snapshot of a typical section of a bridge. We are currently widening. The bridge is getting widened on both sides. Existing structure from beam to beam, and you can see where we shaded the existing bridge railings. We're going to remove the railings, then we're going to extend the deck and put new beams with new substructure underneath. Substructure won't be connected to the existing substructure. We typically don't connect it. We separate the new substructure with existing, but the deck is the only connection point between the existing structure and the new structure or new or widened structure. So that's kind of detail we put in our plans, and this is the deck where we write the traffic vehicle. These are Florida beams looking like an ASHTO girders as well. It's an I shape with 45 in on this bridge. We are using 45-inch deep beams. The beauty about these Florida I beams as compared to the ASHTO beams, the top flange is 4 feet, more than 1 meters. As compared to ASHTO beams, their top flange is roughly 18 inches. So 4 feet is 48 inches. So 18 inches versus 48. So this has a tremendous capacity and can go longer spans as well. That's a comparison between ASHTO and Florida I-beams. This is on the left is 1 feet top flange, and on the right Florida I-beams, I-girders. But Florida came up with extensive research from University of Florida here. They came up with this I-girder which can span longer than ASHTO girders, and it's 4 feet top flange, 3 foot 2 bottom flange, versus 1 foot 6 on the left, for a similar beam depth, 3 feet and 3 feet beam depth. This is what this is FDOT has given us some design aids. They call it some design to kind of see what initially during the bridge development process report. So BDR is a document we put together, and which justifies the type we're going to use, bridge type, whether it's going to be concrete bridge, and within the concrete bridge we evaluate at least 3 alternatives for a new structure, whether it's going to be a multi-span, whether it's going to be 3-span, 4-span structure, whether it's going to be a 2-span structure. Even if it's a 2-span structure, it's going to be concrete or steel bridge, whether it's going to be a longer span steel girder bridge, or whether it's going to be a multi-span concrete bridge. So we evaluate at least 3 alternatives and we do the cost comparison, and those 3 alternatives going to be still the best alternatives among other alternatives, and then we do the cost comparison, and based on the cost comparison and the feasibility of alternative, we propose our recommended structure alternative, which obviously details about the which has a detail about the span length, and the structure type. So FDOT has provided us this design aid for beam. So you can see 36-inch beam, 3-foot depth beam goes all the way up to 100 feet, roughly 30 meters or more. Then they have a beam which is 96-inch, 8 feet girder, almost 2.5 meters. It goes all the way up to 200 feet. And that's what FDOT has done with these float eye beams. They have reinvented eye girders to span longer and to satisfy the needs, because now, earlier what used to be with ASHTO beams, you could not span longer. Those are mainly restricted to 120, 140. So all days we see bridges are 50-foot spans, 40-foot span to 100-foot spans. But now with these FIB beams in last, I would say 12, 13 years, we have seen tremendous change in the industry, at least in Florida. Now with concrete, we can span longer, which provide cost-effective solution, because steel is very expensive. Steel bridges are roughly, if I put a dollar perspective there on a square feet basis, and I apologize, I'm talking about feet and inches here. In terms of, it's $220 per square feet for steel, and concrete is like around $150, $160 per square feet for these type of eye girder bridges. So you can see, like, for every square feet of area, it's roughly $50 expensive. The steel is roughly $50 expensive than the concrete. So with these FIB beams, they have reinvented and reduced the cost of structures big time. So when we do the design, this snapshot on the right shows the load factors. I took it out from the ASHTO code. These are the factors we use. These are the limit states: strength 1, strength 2. There are many strength limit state and extreme limit state in terms of earthquake event we are designing for, or we are designing our substructure for vessel collision force. Florida has a landscape, obviously has tremendous amount of water and bays. So we those bridges over bay and over gulf, we design some of those bridges for vessel collision force. And that force is, I'll relate that force in kips. It's roughly easily around 1,500 to 5,000 kips of force. And it's a tremendous amount of force. So that's the reason it is considered under extreme event with a factor of 1. Dead load has a factor of 1.25, live load is 1.75, and service 3 is for tension. We check it for tensile stresses, is for service 3 combination. Service 1 is for compressive stresses. Strength 1, for strength design, we need to satisfy strength 1, 3, 4, 5, 2, depending on what type of structure we are dealing with. But when the basic design steps are, like, we need to understand, obviously, the typical section. When I say understanding of the typical section, is we need to make sure, we need to first understand what's the width of the structure between the railing to railing, because that will set up the number of lanes you're going to be designing this bridge for. And that's the reason you need to first have a good understanding of your typical section. And then bridge geometry is the next step in the process, like I mentioned. Then we do span length. Now, okay, so you have 120-foot span or 130-foot spans, then you determine the span length. Once the span length is determined, then you define your bearing lines, where bearing is going to be sitting on substructure. that will determine your bearing to bearing distance. And that information is very critical for your beam design, because beam design is from bearing to bearing. Then you, based on the bearing to bearing distance, you're like, okay, fine, now I, depending on design aid, you get a good sense of idea, like whether you're gonna need 7 beams, 8 beams, 9 beams. So you start with something, you have to start with something, and something comes from either your experience or something comes from those design aids. But those design aids are not Bible. Those are just a basic information. So from your experience, you're like, okay, fine, let's try 5 beams. 5 beams may work for this type of a width of a structure and this length of a structure. Once you have the number of beams, you you come up with the load on the superstructure is from railing barrier on the outside. You may have pedestrian sidewalk there, so we define those loads in 2 categories. One is non-composite loads and composite loads. So non-composite loads are the ones which are acting on a non-composite section, which is basically girder by itself. So the loads which are acting on a non-composite section is mainly the stay-in-place form, the form work they use to cast the deck. And that form is attached to the girders, between the girders, so that deck can be cast on top of the beams. And traffic can go underneath as well while deck is being casted. So that stay-in-place form loading is non-composite loading. Then the composite loading, the composite section is when deck is hardened on the girder, that entire section is acting as a composite section. The loads which are acting on a composite section is the railing load, because the bridge railings are put on after the fact. So that's acting on a composite section, and it is called as a composite load. And the reason it's important is because we check different stages, whether the non-composite section is controlling the design. Typically it doesn't, but obviously composite section has a different inertia and properties now. So the stresses are different now. So that's a reason we check different stages to make sure the bridge is designed properly for different stages of the construction. It's very important to make sure to understand the different stages of the construction and to follow through those design checks for different stages of the construction. Sometimes you see that structure is failed on false work. Unfortunately, recently we saw in Calcutta where structure was failed structure was under construction and it was on false work. I don't know what happened there, but false work obviously failed. That those are the things which we need to pay attention to make sure that structure is stable during construction. While the structure is being constructed, the concrete is resting on a false work. As concrete gets hardened, we need to make sure how those stress is going to flow through the structure and how the structure gonna start acting up. So it's very critical for big complex structures like segmental structures, construction on false work, to make sure we account for all those things. Live load is typically moving load. Obviously it's a vehicle which is moving there, so it's either influence line analysis, influence surface analysis, moving load analysis. So those type of analysis we do. Some programs has inbuilt capability. Sometimes we use program like STAD. Here we use mainly larsa 4D, if you have heard about it, lucis, midas. Those type of programs we use to do influence surface and complex analysis, time dependent analysis, pushover analysis. Typically, these eye girders, these concrete beams, we use 8,500 psi concrete. We come up with the strand pattern in the beams to make sure the beam is properly filled in every layer before we go on the top, because the basic concept tells us that the strand has to be far away from the neutral axis to get the maximum capacity out of it. So you want to make sure that you fill the very bottom row of strands first, and then you go close towards the neutral axis. So it's a basic things we have learned and we have studied in our engineering. Shear reinforcement is a key. Sometimes you see the beams are failing in shear near bearings if those reinforcing are not proper. In old beams, we see that the shear reinforcement is spaced at 12 inches to 24 inches, and sometimes over the time those beams develop shear cracks. So it's next couple of slides, a snapshot from Conspan. It's one of the software provided by Bentley, Leap Bridge Suite. So typically these pre-stressed beams, pre-tension beams, we design using Conspan. So you define the geometry. In this particular example run I created, it's 5 beams there. You define the overhang to the left, to the right, and number of beams, give the beam spacing, define the deck thickness, haunch thickness, length of the span, bearing to bearing distance, and then you come up with the material. I didn't print out the material tab. Then loads, you define. So in the loads you see here is precast DC. So it's a non-composite load, and it's a stay-in-place form deck forms. And then the barrier and right barrier is a composite DC. It's acting on a composite section. So it tracks loading based on the different section, and to make sure when we do the stresses computation, we account for right section. Then at the bottom you pick whether you pick the which truck you want, which live load you want to analyze. So typically we do design truck, design tandem. Those are AASHTO notional load for bridge design. Then we when we do the load rating, then we do the load rating for all the other legal loads and permit vehicles. This is where we pick the strands pattern. So as I was saying, that you first want to make sure that the bottom row of strands are completely filled. Neutral axis is somewhere here near the bottom flange, but within the web. So you want to make sure that the bottom row is completely filled. Then you move up to get the biggest bang for the buck there. This keep tracks of the different stresses, service 3, final 1, final 2, final 3. So those are the different stages. And you want to make sure that the structure, the beam is near mid-span, because it's a single span beam, simple span beam, I should say. So you want to make sure that obviously it's below the tensile stress limit. Concrete is not a good intention, so we want to limit those tensile stresses to minimum and within the limits allowed by the code. This is the load rating screen snapshot where you pick different legal loads or permit vehicle depending on your requirements, where you are, whether you are in India or different state in US. Like I said, there is a different loads depending on the local conditions and needs. So every state has their own legal loads and permit loads we need to analyze for. That's a rating output. It shows so moment rating, shear rating. So this particular example, it is designed to 1.08 rating for moment, and for shear, it's a rating of 1.02. There was just an example run I created early this morning to show you the output of what that output rating output looks like. But as soon as you see these numbers, obviously it tells you, like, some designers are good with 1.02. It depends on from designer to designer or to professional engineer to engineer. um, I personally am not comfortable with 1.02. I want to see all these numbers to be at least 1.1, because of to have some additional factor of safety for construction. So the key things I want to cover as well is design consideration. So you're what I always say is, what we do is, our product is our plans, our deliverables to the client. We don't have a product like Apple iPhone or a car. We are not creating a Tesla or anything. What we are doing is, it's our design. Then you need to convey your design. How do you convey your design? You convey your design by putting all of that information on plans. We generate those big plan sheets in AutoCAD or MicroStation software. Nowadays there is a new thing like OBM, Open Bridge Modeler, as well, but it's the same. It's the heart of the software is still MicroStation, um, but you need to make sure your plans are thorough and complete. It's clearly, all the details are clearly shown, and when you do the detailing, you want to make sure there are no conflicts. So I'll follow through some of these slides, and it will give you a perspective of what I'm talking about, why it's so important to make sure that your detail is robust enough to make sure contractor doesn't have any issues in the field. That's what you try to achieve, that he doesn't face any issues due to your design. He may face issues due to his construction method of construction, which is his means and method of construction, we call it. As long as he doesn't face issues with your design, from your design, then at least you are not liable for any construction mishaps or any construction overruns. In case he may find that your design has a flaw in it, you are liable for big damages, and those damages are not just limited to the material. These days we are seeing construct contractors, they don't talk about material anymore, that you need to pay for X pound of steel or X cubic yard of concrete or this and that. No, they are not talking about those. That's just a peanuts in a big grand scheme of thing. What they hit with design firms is delay claims. Those delay claims in delay in procuring the material, the labor is out in the field, construction equipment they borrowed from another firm, all those things get added on top of it. So your basic $10,000 claim just due to the bill of materials and quantities may go up to easily $200,000, roughly 60 lakhs. All right, sorry, 1.6 crores actually, $200,000. So it's a big, even a simple mistake of number of bars in the rebar calculations. If one time we saw where beam length was not computed properly, contractor brought the beams in the field. What happened? He was about to erect the beams, and he found that beam basically passed through between the piers because it was not long enough. And company got a call, is like, what should we do now? Like, we can't delay the construction. Can we utilize this beam somewhere else? We were working on a big billion-dollar project where we were designing 90 plus bridges. So we found a bridge where we could utilize that beam, because obviously we didn't want to waste that material. So we utilized that beam on another bridge, so that he didn't need to cast beam for that particular bridge. But those are the things, like, we try to ensure, and that's where our main focus is nowadays. So we don't do design, is we have to do it as a professional engineers, but now what our main focus is also on ensuring that he does not find a flaw in your design. And that's where I'm saying our plan should be complete. It should be easy to follow. All the details that you show about the bearings, the cross frame spacing, I'm showing the framing plan, the layout of a steel plate girder with cross frame spacings. On this slide, these are lines of cross frames. These longitudinal lines are the steel plate girder, representing steel plate girders. So all these details are properly defined, how these, what's the spacing of the cross frames, what's the spacing of the girders, 9 feet there. So it has to be easy to follow and easy to understand. We try our best. Sometimes obviously we cram up the information too much, but at the same time we try our best to make it still clear. This is a long hammerhead pier, almost 70 feet, so easily 20 plus feet, 20 meter plus cap length. It has tremendous amount of reinforcing in the cap, and I'll show you in the next slide. But look at the geometry information, because client wanted the pier to be aesthetically pleasing, and obviously we as an engineer, we need to abide by what client says eventually. So we came up with this nice architectural curves on these columns and these rustication as well. So with all the geometry information, this sometimes sheet gets busier. This is the reinforcing we put in this column. So the reinforcing we properly defined with the stirrup spacing, and you can see the stirrup spacing is changing depending on the needs. Obviously the spacing, we need tighter spacing near the column, and we can increase the spacing as we go away from the column. So same basic principle of our shear and moment. And these different layers of steel on the top for negative moments, and then positive moment steel. There is no positive moment here because it's a hammerhead pier. It's mainly negative moments. The steel at the bottom is just mainly for shrinkage and temperature. And that's a finished product of the same pier. So it takes a lot of effort to get there. This is abutment. We put it together, the information sitting on piles, steel pipe piles. The cap is cantilevered. There is a roadway underneath, and that's the reason it's not a typical detail. We came up with this detail on all of these things that are on my bridges. I'm showing you all the slides related to projects I signed and sealed and managed. We had two girders cantilevered, and so obviously these piles are needing to be taking a lot of axial force. So we put a cluster of piles here to resist that tremendous amount of axial force coming from this cantilever effect. This is the finished product. Here is a cantilever supporting the two girders and there, and full abutment with 15 feet of cap sticking out. This is straddle bend. Look at the geometry, all the details, all the different dimensions with elevations and everything we mentioned for this straddle bend supporting on two columns. That's the first thing, the geometry. That's what I'm saying. The basic thing for everything is the geometry. What's the elevation? We need to define every single thing so that he knows, contractor knows how to build it. Without these elevations, he doesn't know how to get all these different curves and different depths and details. Then we do the reinforcing. This is a post tension cap. Uh, Reinforcing is pretty critical, and this is not just a day or two-day job. It takes a lot of back and forth markups between the CAD person and the engineer, and engineering is 50% into it, and then detailing how you gonna make sure that there is no rebar conflict, there is no congestion, because you don't want to create a steel frame within the concrete that the concrete cannot pass through these rebars. So you need to make sure that these rebars are properly spaced so that concrete can flow through it for proper consolidation. And that's the reason we make sure that all these details are properly there, and the spacing, you consider different layers of steel to make sure the spacing of 6 inches. By the time you account for different steel layers in the vertical direction, at least the net clear spacing between the rebar is at least 2 inches, 3 inches for concrete to pass through. That's the end section and sections along the cap, like with this inverted T shape where the girders are sitting on either side of these inverted T cap, and with post tensioning ducts running through it. Near the cantilever portion, the ducts come at the top, near the between the columns, because positive moment is controlling there, obviously. So you want to make sure that ducts are running near the bottom face. And that's a finished product of the same detail with inverted T and the solid section with the post tensioning running. So post tensioning start from top there and comes down and goes there. So it's obviously you don't see anything in the finished product, but to get there is it's a engineering what it requires. It's a different view. It's an upstation view of the same pier. So it's supporting singles span on the downstation side, and it's supporting two spans structure on the upstation side. See pier, simple looking detail here with the geometry and all, but when you go to the reinforcing for this, where the girders are casted into the concrete with post tensioning around it to make sure the cap is fully in compression for this tremendous amount of load coming in. With regular reinforcement, we were not able to make it work, so we had to put the post tensioning. So we put in 619 strand tendons to make it work. But all the reinforcing, these tendons are big tendons, so we need to make sure that the force at the end and the concrete can handle that force. So anchor zone reinforcement. So we need to do all the design to make sure the reinforcing is properly reinforced, all the shear reinforcement is properly defined, and sets of the rebar, so that contractor knows how he gonna place these reinforcement. So we go very deep into the detail to make sure contractor knows how each and every single rebar going to be placed. And that's where our next level of engineering comes in, apart from design. I consider detailing is more involved rather than design, because you can design anything, but if it cannot be constructed, it doesn't mean anything at the end of the day. Column, so it's heavily reinforced on the back side. Um, all these bundle bars with another layer of the bar was put in on this big 12 feet by 9 feet column, um, to resist those tensile stresses on this backside. That's a finished product of the same C-pier. Girders into the concrete. Here is the post-tensioning running in it, and that's the backside of the column I was talking about, and I was showing you the detail for. So, what are the key takeaways? So, please, whenever you are involved with, make sure we design smart. Um, by smart design, I mean to say it's constructible. I'm not talking about designing and creating big, nice 3D models. And no, we need to make sure the reinforcement, everything is can be placed properly, and concrete can be consolidated properly, and that in the end the design is constructible. We see from the contractor, contract comes back, I cannot construct this has tremendous amount of steel, reduce the steel, I cannot just pour concrete in it. We need to make sure we design smart, we need to be efficient about our design, provide clear and detailed information. If he cannot understand your plans, then it doesn't mean anything. He will make your life crazy and hell by calling you day and night about each and every information. Can you tell me where is this information? I cannot find it. Can you tell me where can I find this information? This is not clear, can you please clarify? You're going to have tremendous amount of questions, so it's better to take care of those things by providing clear and precise information. Additional factor of safety in design, that's my one of the pet peeves. I tell my staff as well that don't design to a point where it's you feel proud of yourself that yes, I designed to, my design is so efficient right now that it is designed to 1.0 factor. No, it's a stupidity, because I had a case in the field. Unfortunately, that beam was designed with a load rating of 1.02. Contractor came back, is like, in the field, he's looking for additional half inch of buildup. Is nothing. I ran my numbers and I told contractor, do not touch that beam, because as soon as you put in half inch of buildup on it, the rating went down to 0.98. And I was like, it's a new beam. I cannot have a rating on a new beam of 0.98. So what I had, if he would have gone with additional half inch of buildup, I had to tell him to replace the beam. If that half inch of additional buildup or haunch is not avoidable. So that's a reason I always say is please, yes, make sure your design is efficient, make sure your design is competitive. Yes, I get it, but have a little bit of additional safety in it, so that something changes in the field, we need to give contractor a little bit of room as well. You don't expect, we see piles are driven 4 inches out of tolerance. We get a request, you think he gonna pull out the pile from the ground now because he drove that pile 4 inches out of tolerance? No, he's not gonna do it. He gonna send you a request, RFI we call it, request for information. It's like, can I leave this pile? Does your design work now? So we need to make sure we have that additional factor of safety. Completeness in detailing. Don't just simply say like, okay, I have shear stirrup from there to there at 6 inches and go home and be done with it. No, you need to make sure that those every single thing, there is no conflict. So it needs to be properly detailed. So make sure there is no congestion in the rebar. One important thing is bill of material. It's the most important thing for us designers. Any mistake in bill of material and concrete quantities is a recipe for big claim. We have seen cases, we make mistakes, we are humans. I've seen people making mistakes like sometimes the reinforcement quantity is just half. I gave you an example of the beam length. How can you miss the beam length that the beam length is less than what's needed? But it happens because we are humans, we make mistakes. But that's the reason it's important to make sure that your design is going through proper detail checking process and QC process, we call it. So every design goes through from designer who does the design to a checker, we call it, another senior engineer, another competent engineer does the checking of the design calculation, and then there is a third person who does the QC. After all of this process, still few things slip through the crack as well. But hey, again, we are humans. And make sure you have adequate notes and information for contractor on the plan so that he can refer back to different sheets or the information you think he would need to finish his work. So with that, I'll open the floor for questions.